All right, so let's have a look at the exercise number 6 for this week, doing data analysis with NumPy. And, well, in general, the problem for this week, or what we're dealing with, is we have some daily temperature observation data from the Helsinki-Vantaa airport. And we've got observations that go back for something like 60 or maybe even a bit more than that years. So these are in a data file, same kind of format we actually worked with in the lesson this week, so that's nice. Should have some pretty good ideas of how to get the data loaded in. And we've got temperatures in Fahrenheit like we did before. Same kind of columns, station names, basic information about the geographic location, date of the measurements, and then things like precipitation, average temperature, max, and min. This should all look fairly familiar. And if you want more information, of course, there are links from the exercise that will take you to the website where the data was, from where we downloaded the data, and you can kind of have a look around there if you'd like. We have 3 problems that are included in the exercise for this week. And then there is one extra problem if you're looking for something additional to do that won't affect your grade, but just if you want to have an extra task, you can feel free to take a look at problem number 4. We'll focus here on problems 1 through 3, and I'm just going to preview this in GitHub. So we'll see our Jupyter notebook is rendered by GitHub, and the stuff you've just seen is basically showing up here at the top. If we scroll down to problem number 1, our first task is to read in a tricky data file. Well, it's not that tricky. We've already read in this kind of data file once before, but in the data directory, you'll find our data file for this exercise. And we're going to read it in using np.gen from text like we did previously. Okay. All we want to pull out of here are the columns for date, precipitation, and then the 3 temperature columns, and read those in as numerical values. You shouldn't have to do anything special other than tell which columns to use when you read the data file. We'll skip the header like we have before, and then we've got the job of converting these no data values, the -9999, to NaN in NumPy, and we saw how to do that in a lesson this week, so hopefully these first few steps you can move through without too much difficulty. When we read the data file in here, the first part of the problem, we're going to skip the first 2 rows. That's the header. We're going to read only these columns we just mentioned and convert the NaN values. And then we're also going to split the data into 1D NumPy arrays called date, precip, tav, tmax, and tmin. And I would say that it's important to use these names for the arrays for each column, because when the auto grading runs for the exercises, it checks to see that these variables exist. So you should use these variable names. Now, I would suggest that you do this in this order. We can convert all of the no data values into NaN first and then split. It'll be easier than if you do it the other way around. If you split them, then you've got to go through each one of those arrays and convert the NaNs. So you should think about doing it in this order. So you'll put your code in here like normal, and then we're going to have some basic questions here, like how many no data values are there for t-average? How many are there for t-min? How many days do we have in the data file? So these are basic observations, basic things that we can extract from the data that we've just read in. First observation, last observation, average temperature for the whole data set. And in this case, you should be using the t-average column. And then what is the tmax temperature for the summer of 1969? And so that would be the months of May, June, July, and August. Normally, June, July, August, it's what's used for summer, but we'll add May in there just for the heck of it. And then we'll store that variable as average AVG temp 69, and then you can put that code in to do that stuff there. So the first problem is really just reading in the data file and getting some basic information about what kind of data we're dealing with and the temperature values. Problem 2 moves on to calculating monthly average temperatures. So what we want to do here is create a NumPy array called temp monthly. And we're going to go then in this temp monthly and calculate the monthly average temperature for each month between 1952 and 2016. This is not the full range of data that we have in terms of, like, there are some data values from 2017, but you should only deal with 1952 to 2016. And we're going to calculate for those years the monthly temperature of January, February, March, April, May, June, July, August. All of the different months for 1952, then the same thing for 1953, 1954. So this is going to be a longer array. It's going to be an array that is the length of the total number of months we have within our data from 1952 to 2016. We're going to do this using t-average, TAVG, that variable. And I want you to be aware that there is missing data for several years in TAVG. So if you create the array where you want to store this, for instance, to say, like, let's take the difference in years between 2016 minus 1952, how many years is that? Multiply that by 12 to make our array. You're going to have a lot of zeros left over, for instance, at the end of the array if you use NP zeros to create it, because there's missing data for something like 8 or 9 years in here for TAVG. So something to be aware of, and we can maybe add a hint about how to handle this situation if you're having a difficult time with that. Once you've got your temp monthly, so monthly temperatures for that range of years, we'll convert that to Celsius, just like we did during the lecture, and then just save your changes to GitHub. Of course, you should be saving them along the way, but ultimately we want to make sure that you end up with your updated notebook in your repository for this week's exercise. Problem 3 then comes to calculating the temperature anomalies for each month. So we're going to look at how much the monthly temperature deviates from the average that's calculated in this part, in problem number 3. So what we want to end up with here is an array called ref temps, and ref temps should be 12 values long. It's going to be one value for each of the months where we get the average temperature for that month from the period of 1952 to 1980. And so what that means is, like, you'll take January for 1952 to 1980, add those values together or sum them in some way to calculate the mean for that time period. You could use a mask, for instance, and then just do dot mean of whatever values you get for January between 1952 and 1980. We saw a bit of how to do this in class, so hopefully that's something that is you find a solution for without too much difficulty. And in the end, essentially what we kind of want to end up with something is an array called unique months that should just be the string for each of the months from the first month of the year to the 12th, and then the corresponding reference temperatures for those months. So these would be the average temperature for that month during the reference time period. Once we have that, we can calculate the temperature anomaly for each of the months that we have in our temp month Celsius array. So remember that temp reference temps or ref temps, this array should then be temperatures in Celsius. If you put it, leave it as Fahrenheit temperature, for instance, then you're going to have trouble. But what we want to do is calculate the temperature anomaly for each month in temp monthly Celsius. Temp monthly Celsius is the array that has our monthly average temperatures between 1952 and 2016. So we want to see then for each month, how does it compare to the long-term average from 1952 to 1980, and see whether there's any kind of trend in there. So we'll have these three arrays, one called anomaly, one called unique month, and one called ref temps. hopefully you've got some idea where those things come from. You'll put the code in here, and then you're going to be asked, what is the largest value in the anomaly array, and otherwise, that's essentially what you have to do here. We're going to update your notebook as always. Save your changes to GitHub, and that should be that. That's what you have to do. That's the exercise for this week. For exercise 6. Problem number 4, if you're interested in doing it, is basically repeating the same kind of thing we've just done, but for a different location. So going to the Sodankylä climate station, and again, reading in the data file, basically doing the same kind of processing we've done to calculate these temperature anomalies. And in this case, for Sodankylä, there's a little bit of a tricky situation here in that there are no TAVG values, or it's all missing data. So we're going to have to calculate a T-average ourselves by just taking the difference between the maximum and minimum temperature. It's not exactly the same as the average temperature during the day, but it's best we can do in this situation with missing data. Then you'd go through the same process of calculating things like the temperature anomalies, and then there's a few questions here to compare the observations for instance, summer temperatures between Sodankylä and Helsinki. So we could see, do we have similar temperatures? Are the temperatures warmer in one place than the other? Things like that. And does it make sense, how the temperatures vary? This is an optional thing. And so, you could basically plan on doing the same kind of steps you've done in mainly problems 2 and 3, adding some cells to this Jupyter notebook and uploading it to GitHub. And yeah, it's up to you if you feel like you've got time to do something like that. Otherwise, good luck with the exercise this week, and if you've got questions, we'll be at the work sessions and on Slack to help with answering those.